All right, so today we are happy to have Sebastian Falkensteiner from the Max Planck Institute in Leipzig, and he will speak on transforming radical differential equations into algebraic differential equations.
So first of all, thank you very much for the invitation and the opportunity to speak in the Colchin seminar, and also the introduction. So yeah, as mentioned, I want to speak about transforming differential equations involving radical expressions into algebraic differential equations. And yeah, so this is a short outline, but yeah, we will see what's going on in this topic. So for example, we have this differential equation here, which has a radical expression and the coefficient. So here we have x plus 1 and the root of it, the square root. So we want to look for a solution y of x of this ordinary differential equation. We can enter this, for example, in Maple and take a look what the dsolve command gives us. So here you can probably see small how solutions look like. So we have a trivial solution, a family of solutions, and a very ugly other family of solutions. But okay, we have this as an output, but I claim that not all solutions are given with this answer. How to find this missing family of solutions? So if we take x and replace it by z square minus 1, the reason is we want to get rid of the square root here. We additionally have to replace the y of x by some capital Y of z accordingly, and yeah, we also have to take care of the derivative. So if we are doing it, the original differential equation transforms into this differential equation, which doesn't...
Sebastian, quick question.
Yes.
Where did the original equation come from?
It was in Colchin, in Kampke's book, and I don't know how exactly the motivation is given there. I think it's somehow from physics, but I don't remember how exactly.
Okay, thank you.
Okay, so in this differential equation here, there are no radical expressions anymore. So we call this type of differential equations algebraic differential equations, where everything is polynomial. And now we can again plug it into Maple, and it gives us this solution back here. And now we have a solution, capital Y of z, so we have to transform it back. But yeah, this is a very easy transformation. So we just replace the z by the square root of x plus 1, and we get this solution here. And this was not detected in the solutions found by Maple previously. So here, maybe just to see it. Okay, and now we want to have a mathematical theory around this procedure, which we saw.
And by the way, the solution that you found after this transformation, you found all solutions?
So this is a general solution of an algebraic differential equation. So it, in principle, could be the case that there are some singular solutions missing, and you can take a closer look to the differential equation if there are some singular solutions. I guess there is no singular solution except the constant 0, but it could be another constant solution or something like this.
excuse me. What is
Yes.
the underbar here mean?
Okay, I used the notation from Maple here, where we have an arbitrary coefficient.
Oh, okay. All right.
So the C is already a coefficient in the equation, and this is why the C, as it usually does in Maple, for such free parameters, does not appear. Instead, we are having underscore A. Yeah. Thanks for the question.
Sorry to interrupt. So does it appear that you don't recover the other solutions here when you did that process? The other
solutions appear as well. I didn't put the Maple output again because it was very long.
Yeah, thank you.
And Maple didn't find a zero solution.
It found, so for this transformed equation, it found all solutions here plus additionally this solution. Yeah. Okay, so for having a theory around this, we work with radical varieties and radical parametrizations. And we want to decide, or in the affirmative case, give a transformation starting from a differential equation involving radical expressions into or getting another system, maybe even of differential equations, which is just algebraic. So no radicals are involved anymore. Okay, and for this, we start by...
Okay, so is these radical expressions involving only the coefficients, or did it also involve the unknown y?
We will come to this.
Okay, thank you.
Okay, so first we start with the notion of radical parametrizations. So a radical parametrization is a parametrization is a tuple with which has a rank. The Jacobian has sufficiently high rank, and informally speaking, it consists of repeated applications of addition, multiplication, and taking roots. So something like this here. For a very formal and precise construction, we work with field extensions, or actually a tower of field extensions, such as this one. And we usually start with the complex numbers plus the parameters we will use for the parametrization. And then, so in this tower field extension, we always add one radical expression for getting to the next level. And this will be denoted by delta. And yeah, so as I said, a parametrization has to be a zero of the defining polynomials, and the Jacobian has to have a full rank. So the rank has to of the Jacobian matrix has to be equal to the number of parameters. Okay, so we take a look, for example, to this radical parametrization, and we take this root here, encoded here with delta 1, and then this root involving the delta 1 for getting delta 2 and the tower, which is written here. So with this deltas written here, with this expressions and equalities, we are not done yet. So we also have to clarify which branch we take, which is basically seen here, but not here anymore. So this can be done, for example, by just writing one value, which is not the branching point. And then the radical parametrization can also be written in this way. But so the important thing is we have to fix the tower where we consider the radical parametrization. And so choosing the tower is non-unique. Okay, so having now such a tower of field extensions and the chosen deltas, so I denote delta bar the tuple of all the deltas, we can rationally write the parametrization in the deltas. Okay, and to proceed, we collect all this data about the deltas in the incidence variety. So this is given by, we take all the parameter values of the given radical parametrization. We take the list of the deltas and we write the parametrization rationally in the deltas. Okay, and this gives us a map phi, and we consider the image of this map and take the Zariski closure of this image. This gives us an algebraic set, a variety. It's irreducible. Yeah. Okay, and this incidence variety we will write as BP. And so we are interested in the last component here because we want to take a look to the variety defined by the radical parametrization. And this will be found by taking a projection of the incidence variety. And the other components will also be important. They will be also found by a projection. So if this was too fast, here is a picture of this process. So here we have the parameter values. And we have the given radical parametrization P. And the image of it, this will be the radical variety. So but this cannot be given directly. So we have to follow this procedure I showed. We collect all the deltas and express the parametrization rationally in the deltas. So this is going up from the parameter values to such a variety Vt, which is called the tower variety, and then further or directly use this map I showed you on the previous slide. And then we can take projections to go back to these two varieties, and they will be very important for us. So this tower variety giving us the parameter values and the radical expressions, and the radical variety, which is the image basically of the given radical parametrization, they are very important for us. And also of importance will be the tracing index of the given parametrization. So defining a tracing index of a rational parametrization is very straightforward, but for radical parametrizations it's not so easy. So we do it in this way of going to this incidence variety, having all the information, and then taking a look to the degree of the projection. Okay. So coming back to the example from before, if we have given this radical parametrization over this tower, we want to compute the tower variety and the radical variety. So the tower variety, this is easy. We just take these equations here, defining the tower, and take the zero set of it. That's the Tau variety.
And a quick question. So what you're doing here, is it completely unrelated to the differential equation structure?
So far, yes.
Thank you.
Okay, now we want to get the incidence variety. So we add to these equations, we add the defining equation or the implicit equations of the parametrization. So x1 equals to the first component, x2 equals to the second component, and the denominator should be non-zero. And this is how we find the incidence variety. And then we compute the elimination ideal via Gröbner basis. And in this way, find the radical variety. So this parametrization here is a parametrization of this variety. This is basically implicitizing of the given parametrization. And now the question is, can we replace this radical parametrization P by a rational parametrization Q? Because rational parametrizations have some advantages compared to radical parametrizations. For this, I want to say that these two varieties, the radical variety and the Tau variety, are very much related. So they are both irreducible and have the same dimension. And even more, they are birationally equivalent in the generic case where the tracing index of the given radical parametrization is 1. Okay, and how can we relate them? If we find a rational parametrization of the Tau variety, and remember the Tau variety is very easy to compute, then we can get the rational parametrization of the radical variety. So we just take this here, and this mapping size is just a projection. So, or the inverse, sorry. The inverse of it is just a projection. So that's nothing dramatic here. Okay, so we would not have to compute the implicit formulation of the radical variety. We could directly try to find the rational parametrization of the Tau variety instead. And this is sufficient and also necessary. Okay, and algorithmically, this will always be possible if the dimension is not too big, meaning not bigger than 2. So coming back to this example where the dimension is 1, we have given the Tau variety from the radical parametrization, and this can be parametrized. You can use, for example, Maple if you want to do so. And then we take the projection, that is this psi inverse here, and in this way get the rational parametrization of the radical variety. So basically we can work with this rational parametrization Q instead of P. Okay. Now we want to go one step further and coming from algebraic equations and parametrizations to differential equations. The first step is we want to take a look when in the coefficients in the x are radical expressions involved, like in the multi-weighting example. So we define again a radical tower and we choose as a base field this here, where x is the independent variable. So we have given one single ODE, but it could be a system of PDEs if you want. the most complicated object, involving radical expressions in X. So we can write F in this way, where Fm is built in this tower of field extensions. And we want to find a change of variables. X equals R of Z, and all the other things are changed accordingly, such that the transformed equation is algebraic. So it can be written in this way. So here, the coefficients are rationally or polynomial, if you want to, in the coefficient set now. Okay, so what we do is we treat this ODE similarly to the case of radical parametrizations. And by some version of the main theorem we saw in the beginning for radical parametrizations, we can prove the following. So if the tau variety is rational, so previously we had that if the tau variety is rational, we can find a rational parametrization instead of the radical parametrization. So we want to do the same with the radical differential equation now. And indeed, there is a rational transformation of this type doing that if the tau variety is rational, and if we compute a rational parametrization, so it could be unirational, it doesn't have to be birational a priori, then the transformation is given as a projection of this parametrization, namely it's exactly the first component. And this transformation is in a way that every solution of the original radical differential equation is a solution of the transformed differential equation, and vice versa if we found a birational parametrization. So in our case right now, the dimension is 1. So that's not a problem. We can here always find a birational parametrization if there exists a unirational one. So we have a one-to-one correspondence between the solutions, and we have a criteria to say when we can perform such a transformation, namely exactly when the tau variety is rational. And the transformation is, not, I mean, it can be just read off the parametrization of the tau variety. So it's, let's say, not so extremely hard to find, not harder than finding a rational parametrization of a curve.
Excuse me, when you have a rational parametrization of a surface, typically there are some curves which are not attained by this parametrization, and maybe with bad luck could be solutions.
So this here is a parametrization of a space curve. So it's high dimensional in the sense that it's embedded, so this curve lives in a high dimensional space, but in the case of ordinary differential equations, like we are here, it's always a curve. And this has, so this dimension is, so it's always a curve. And we do not lose any solutions or something like this, because they would just be points. And how to say? So it's not the case. Let's say it like this. It's not the case that the dimension or that this variety corresponds to solutions of the differential equations. So it's more about the finding the transformation which is suitable. And does this answer the question?
still not sure that this transformation does not lose this kind of special solution. So if I have an algebraic variety, when I rationally parameterize it, I can lose some points. This is almost surjective, not perfect.
But the solutions will depend on X, not on, and they are written in X and not for X equals some value. So we will see that solutions can be lost later, but not if the radicals appear just in the coefficients.
Ah, okay. And by the way, another question: in this situation, can we rewrite the equation as a resolved equation? I mean, y prime as a rational expression in the other variable, or
not necessarily.
not
So they will be, in principle, they are algebraic differential equations, meaning they can be written as a polynomial in y and its derivatives and x or z. Or in this
when
case,
the discriminant in the y prime of the equation vanishes, there will be some special solution, maybe.
I mean, there is a lot of theory on algebraic differential equations, and when they can be transformed into explicit form, for example. But we do not treat here this question of solvability. So we just see that there is much more theory on algebraic differential equations than on radical differential equations.
Continue. Sorry to interrupt.
No problem. Okay, so here I outline an algorithm how to find the transformation. So you choose all the radical expressions, build a tau variety with it, and then try to find the parametrization of the tau variety, which does not necessarily always exist. If it exists, then you can find the transformation. So
and,
here,
and how do you check that it's rational?
it's a curve, so there are algorithms for doing that. So let us consider this easy differential equation, relatively involving unradical coefficients, which we had in the beginning. So we choose this radical expression, get this radical parametrization, this tower, and then we compute a rational parametrization of it, which is very easy, and we find the transformation as suggested in the very beginning. If we slightly modify this example and add here a second root of a slightly different type than this one, then we have this radical parametrization of a space curve built with this tower, and here this variety, you can check it by hand if you want to do so, but maybe for now you just believe me, this cannot be rationally parametrized. So here, for this differential equation, in the setting we are working in, there cannot be found any rational transformation turning f into an algebraic differential equation. Okay, and all these results I showed you for the coefficients.
Sorry, a quick question.
Yes.
So is there some way to tell when this can be converted to rational equation in your previous slide? Sometimes you can, sometimes you cannot, right? So there are kind of general results on when this can happen, when this cannot happen. So
you mean that you have a big family of differential equations where you can say directly from the beginning.
Right, so some kind of
okay.
general result.
I didn't think about this yet, but I assume that you can write or build big classes where you can either always find the transformation or never. I guess so, yeah.
Okay, all right, thank you.
Okay, now, so coming back to one question in the beginning, do the radicals always have to appear in the coefficients? Oh, sorry, this slide I was missing. Yeah, so it can be generalized in principle to higher dimensions, but in the case of PDEs, you have to be careful that not everything is algorithmic anymore, because the theory and the algorithms for finding rational parametrizations of big high dimensional objects do not exist. Okay, so now we move to radical expressions in the independent variables and the y's. And yeah, everything can be now done again for systems and PDEs, but we will stay with one single differential equation, which is given. So this is the F again. And the radical tower is now built over the y's. So here I write y0 up to ys, but yeah, you can replace y0 by y and the s derivative here. But I just want to emphasize that this construction here is purely algebraic. No differential things are involved. Okay, and so we have an equation given here. So the radical expressions do not mix x and y's. So here we just have radical expressions in the y's and not in the x. Okay, and we now want to find a rational change of variables in this y's. So we want to replace y0 by some rational functions in z0 up to zs. y1 with rational function in z0 up to zs, and so on. Which means we completely forget a priori about the differential relation, namely that y0, the derivative of it is equal to y1, and so on. And in order to do that, on the transformed side, we have to keep these equations that the derivative of the second component is equal, the derivative of the first component is equal to the second component, and so on. So this is here encoded, and this will always be an algebraic differential equation. And then the first equation after the transformation, we want to get it algebraic as before. Okay. So the problem is we start from one single equation and move to a system. So if you start with a system, okay, then you say you still have a system, but it's not so problematic as you think, maybe. So here, this has a very particular structure. So here will be just one derivative in the set involved, and so the degree of this derivatives is 1. So we can often solve this lower part for the derivatives in Z and again include it in the transformed equation of F. So it's not so bad as it looks in the beginning. Let's say it like this. So there's additionally, let's say, problem with denominators. So we want to just consider the numerators, and therefore we have to ensure that the denominators are non-zero. But in most cases, or for most solutions, this won't happen. And so we can clean denominators and just consider the numerators. And then for this system, capital G, we can use some maybe some simplifications, such as the Thomas decomposition or regular chains or something like this. Okay, so when do we obtain an algebraic system G? The answer is similar to before. So we take a look to a tau variety, and if it's rational, so having a rational parametrization here, then the resulting system will be algebraic again. Moreover, every solution of this algebraic system can be transformed to a solution of the original equation F. And if this parametrization is invertible, so if this is birational, not only unirational, then also the other way, so then also a solution of F can be lifted to a solution of G, as long as everything here, so all the denominators basically, are well defined. So in this sense, we might lose some particular solutions. Never some version of a general solution, but some particular solutions might be missed. Okay. And yeah, so here now we have n components, and n now is the order of the given equation S plus 1. So this is a very high dimensional object. And we want to look for a rational parametrization of such a high dimensional object. This is in principle not algorithmic at all. But there are two cases which appear regularly in examples in the literature. So the radicals in most cases not appear in all of the derivatives of y. So most of the cases it's just a subset of the variables. Or at least it is the case that we can find a partition of the variables where the radicals appear. So maybe we have the square root of y plus y prime, and I don't know, the third root of the second derivative of y plus the third derivative of y. So then we can form a partition and do as before, iteratively. Okay, and in these two particular cases, or if this appears, then we can move to a lower dimension, namely just to the dimension of the maximum of the dimensions of the partitions, or the dimension of the subset. And besides this, it's very similar to before. We collect radical expressions and then try to find such a partition or subset, then consider all the tau varieties, try to compute rational parametrizations of all of them, and then use the transformations we obtain from the rational parametrizations. This way we get a system, and then we want to simplify this system. So let us take a look to this system here of differential equations in y1, y1 prime, y2, y2 prime. So here we have several radical expressions, and the nice thing is we can take a partition C1, C2, and C3, C4. The tau varieties which appear in this way are relatively easy to parametrize. So the first one can be parametrized as this. The second one as this. So we apply the transformations coming, so the first two components always. So this is given now as this transformation, and we obtain this system here. So this system here can be written. So here you see the derivatives. It can be written in explicit form in this derivatives, and in this way we can also apply some numerical methods if we want to do so. Okay, so what I want to mention is, in this approach, it's not the case that you simply replace every radical expression by a new variable. So you want to find a minimal number of new variables you have to introduce for this substitution, basically.
Why?
Yeah, the reason is the dimension would grow with every radical expression by 1. And then you run into algorithmic problems very fast. So first of all, for finding parametrizations of an even much higher dimensional object, and also the simplification step gets almost impossible to be performed. So for this example, G would not be found with such a naive approach. I ran it 2 days with differential Thomas, even for this G, which is already much simplified, it could not terminate. So yeah. Okay, and now I want to conclude that we can work with differential equations involving radicals in X and radicals in the Y's, but the radicals are not allowed to appear in both at the same time. So they have to be separated. But something like this is still okay. So the square root is not allowed to be, I don't know, X plus Y double prime, for example. This wouldn't be allowed, but this here is fine. This is the Thomas Fermi equation, which is maybe relatively popular among physicists. Okay, then we apply a transformation first on the X variables, on the X variable, and then on the Y's. And here we have this relation which allows us to simplify the obtained system G again to one single equation, which is here. And this equation can be solved, for example, by using the Newton polygon method. And in this way, we found all the formal Pursue series solutions with this initial condition, which is interesting for physicists, apparently. Okay, and here from this solution of the algebraic differential equation, we can easily move back to the solutions of the Thomas Fermi equation. Okay. There are several open questions with radical algebraic equations and parametrization, but also on the differential side. And here I list a few. So the first 3 are basically working on generalizations, and the third one, which properties are preserved. For example, I started to study a little bit that quasi-linearity is preserved in most cases, but not in all. And so I want to give criterion on this. And then another question is, can we find another similar approach for reducing the degree of a given differential equation, which is already algebraic, but we want to find another system which has lower degrees, so the exponents are smaller. It seems to be of interest, for example, in dynamical systems. Okay, and with this I want to conclude my talk. Thanks for the attention.
Right, thank you so much, Sebastian, for the very nice talk. Are there any questions or comments? You can just unmute yourself and ask, or type in the chat.
I have a question, Sebastian. Let's come back to the first problem that you consider, that trying to transform radical differential equation which the radical appears only on the coefficient. Is it correct? Is it correct that if I say your methods will be successful if and only if the Tower variety VT irrational?
Exactly, this is the case. And it doesn't matter which Tower variety you choose, as long as it's minimal, because we have that the radical variety and the Tower variety are birationally equivalent. So in particular, all of the Tower varieties are birationally equivalent. Yeah.
Okay, another relating question. If we are given a radical differential equation of that form, that means the radical appears only on the coefficient only, then it's always we are always in the case that the Tower variety VT is computable from the original equation, right?
Yes, so you just have to collect all the radical expressions and use this deltas in order to have a minimal representation of the tower, but this is algorithmic, yes.
Okay, that's correct. That means we have a sufficient and a necessary and sufficient condition to decide when your method success. And I guess this answered the question by Professor Li Gu.
But so one has to be careful which type of transformations you allow. So we only allow rational transformations in the x variable, which gives a one-to-one correspondence between solutions. So if you slightly adapt the setting and, I don't know, allow here radical transformations, or even, I don't know, involving exponentials or something like this, then we cannot give an answer with this algorithm.
Understand. Thank you.
Any more questions or comments?
Yeah, sorry, it's me again. So just to make sure, right, it must be a trivial question. So if you, without the differential setting, so any radical algebraic equation can be converted to a rational.
Not every. The Tower variety has to be rationally parametrizable.
Okay.
Which is somehow relatively strict assumption by thinking on algebraic curves which are rationally parametrizable or not. So there are, yes, if you take an arbitrary curve, somehow there is no reason why it should be rationally parametrizable. But in nature and so on, there appear a lot of algebraic curves which are actually rational. And also, if I take a look to, I don't know, Kamke's collection or something like this, there are a lot of radical differential equations. And I think, if I remember correctly, around 80% of them could be transformed to an algebraic differential equation.
Excuse me, if I remember well, there is a result that a curve which can be parameterized with radicals, it should have a genus less than 6 or something like this. So already being parameterized by radical, it's already exceptional somehow.
You're right, yes.
Okay, thanks. Yeah, thank you.
Any more questions or comments?
Maybe I have one more question on the neighbor way that Sebastian talked on the very last slide. I think there is another neighbor way to do the transformation here, that you move everything without radical sign on the left and everything with the radical sign on the right, and then do some power in a skillful way, maybe several times to make every radical sign disappear. This is another neighbor way. Is there any disadvantages of this neighbor way in comparison with your methods?
Yeah, so this is basically trying to find a parametrization of the Tor variety in a try and error method. What you are describing. And it can fail in the end. It might be that it's not working in this way, and certainly it will not work in this way if the Tor variety is not rational.
Okay. Okay. Thank you.
Okay, any other questions? So if this is not the case, then let's thank Sebastian again for the nice talk, and I hope to see you all again next week.